All right. Is it an A? All right, let's get it right. If we're going to hashtag it, we might as well be on the same page too. Welcome back to the drive-through, a special post-holiday edition of the drive-through, sponsored by the deli. Hungry? Stop by the deli and get yourself some deer chili. Okay, we are dealing with Lagrange multipliers today. If you're wondering, these were discovered, according to your book, in like 1745 or so. So, I don't know, like 50 years after calculus was discovered. This smart French guy figured this out when he was 19. 1755, okay? All right, so this is an additional way to solve a constrained optimization problem. What does that mean? We have a Shackle equation that holds us back, and then we have another equation involving the same variables that we want to either maximize or minimize. So in that sense, it's no different than what we learned last time. The nice thing is we're not limited to only two variables. So if you remember the second derivative test, that only worked if we were dealing with a function of x and y's. Now we can have more than two variables, although it'll get ugly. Okay, and I will try to explain later in the video when you will use these Lagrange multipliers or hashtag Lagrangipliers, as we will call them from here on out. Okay, but before we go into the process, I want you to take a look at this problem. What if I wanted to find the biggest rectangle that could be inscribed into the ellipse right here? So we'd be at 3, 0, negative 3, 0, 4, 0, 0, 4, excuse me. And I know that doesn't really look like an ellipse, but it is. Okay, so what if we wanted to maximize or find the rectangle with the biggest area located somewhere inscribed on the inside of our kind of ellipse thing? Okay. Well, recognize that any point on this ellipse would be x comma y, if that's what we called it. Then the area of this rectangle, so you get to that, would be 2x wide and 2y high. Does that make sense? So the area equation of the rectangle would be 2x times 2y, which is 4xy. So what we have here is a constrained optimization problem. You could do this without any multivariable calculus. You could just substitute in, solve for x in this equation, okay, substitute it in for x in this equation or for y in this equation, and actually you would just need your old school BC calculus optimize. So we don't have to do it this way, but this is the best way I can explain to you-ish what the process of Lagrange multipliers is doing. Okay, so we have area equals 4xy. You could also think about this in terms of level curves. Okay? So instead of thinking about area in terms of 4xy, if you thought about level curves with 4xy, what you would get, if you just think about how you would write that, y equals c over 4x, right? So those would be a bunch of hyperbolas. Is that right? Am I using the right verbiage? They could both be negative, right? But we're not going to care about the negative ones, I can tell you that much. But yeah, we're going to have a bunch of hyperbolas. So now what I want you to think about is only one of those hyperbolas would be tangent to our constraint equation. The blue ellipse represents our constraint equation. Okay? You can think about these level curves as if you called this function f of x comma y equals 4xy. Now that thing is a surface, okay? And its level curves would look like hyperbolas. Does that make sense so far? Well, how would we know when the two surfaces were tangent to each other? That would happen when their gradients formed a straight line. Could you imagine that? And how would we know their gradients were a straight line? If one of the gradients was a scalar multiple of the other. So that's just the start of this. I didn't prove anything to you. I didn't explain to you why these work perfectly, but I'm telling you that what you're doing is finding out a value, c, that we could multiply this function's gradient by so that the two gradient features were tangent at the same time. Okay, so we just took a little pause. You'll see I circled this. This is my best attempt at explaining why this works, and I'm not great at this, okay? Our constraint equation in this is represented by our blue ellipse. It cannot move. It is our constraint. It's what it is, okay? The area of our rectangle, which is represented by this, hopefully you can see that you could also write that formula like that, and as the value of c changed, we would get many different hyperbolas. So that's what these things are representing. The different outcomes of that equation when we change our value for c. Now, we would have another hyperbola that was right there. Okay, so I should leave it there. We would have another hyperbola that's way over here and would barely look like a hyperbola. Okay? This hyperbola here would give us a tremendous amount of area. However, that area would be way bigger than any area that we could get for the area of that rectangle. As these hyperbolas approach our constraint equation, they start to get closer and closer to the optimized area. When they get to this point right here, our level curve is tangent to our constraint equation. How do we know things are tangent? Again, I'm kind of repeating myself here, but that's okay. Well, we know that two things are tangent if their tangent lines are parallel, or if their tangent vectors are scalar multiples. Okay? And how do we know, how do we find a tangent vector to a level curve? We use gradients. So, I don't know, that's a whole lot of information that we've learned wrapped into itself. This hyperbola here that actually cuts through our ellipse at 2 points would actually represent an answer that gives us an amount of area that is not optimized. And I think it means there's two different ways, or two different values of x and y that we could choose to get that same area. Okay, so there's only one value for c. Well, hold on, let me put that. Who took my pink? There's only one value for c where if we choose that value, it gives us this tangent level curve. And that value for c is going to be our Lagrange multiplier. Okay? So here's what we're going to do. We're going to come back to this. We're going to fast forward, and we're going to learn how. So we're going to learn the method of Lagrange multipliers. Method of Lagrangipliers. So first, we need f of x comma y, and it could be more than that. It could be x, y, z. We need this to be a function with an extrema. Okay, so in this case, f of x comma y is our function that we are trying to optimize, and our book refers to that as the objective function. Meaning we are trying to make it as big as possible or as small as possible. Okay? G is going to be a function of the same variables. That's very important. So I could have a little dot, dot, dot here as well. And this is our constraint equation. Okay? And so that is going to equal C, some constant. Where's the function at? Oh, function? Function. It's like a function made out of onion rings. Okay? Alright, so the first thing that we do is you set up, in this case it would be 3 equations. You would say let f sub x equal to some constant. So instead of referring that as c now, we're just going to call it lambda. The lambda is our Lagrangiplier. So f sub x is equal to lambda times g sub x. F sub y is equal to that same lambda times g sub y. So we multiply our constant times our objective function. No. Sorry. We are multiplying our constraint function by the lambda. And then you have your original equation, g of x comma y equals c. And what that's going to eventually do is give us the same amount of variables as we have equations. Okay? Also, I want you to keep in mind that the gradient of g is just equal to g sub x plus g sub xi plus g sub y j. So that's why these things are coming from the gradient. Okay? So this right here is how you set up the Lagrange multiplier problems. Once you set them up, you solve them. The easiest way or the most consistent way to solve them is to solve each of the first 2 equations for lambda and then plug, and then you'll be able to identify one y in terms of x and plug that back into this. You'll see it coming up. Okay? Then you simply test the points into our original, let's see, objective function and find the biggest one or the smallest one depending on what you're looking for. So let's see if I can tackle this problem now. Okay, so let's see. What is our f of x comma y? Which function is that? Okay, that's right. All right, that's our that's our objective. And what are we trying to do? We're trying to maximize that thing in this problem, okay? Right. And then they call it, instead of optimization, they're calling it the objective function. Okay? So what is our g of x comma y? x squared over 9 plus y squared over 16 minus 1. Okay? That is our constraint equation. And I know that I want to do, so what is our f sub x? It's 4y, right? Just simply our f sub x and our f sub y. I'm just doing calculus right now. 4x and our g sub x. Our g sub x. Yep. 2x over 9. And our g sub y. Y over 8. Okay? Alright, so now I'll set up my Lagrange equations using my Lagrange multiplier. So, I can say 4y is equal to lambda times 2x over 9. So, lambda 2x over 9, I wrote that huge. That's one equation. Okay, what's my next equation? 4x equals y lambda over 8. And then my final equation goes not this one per se, but back to x squared over 9 plus y squared over 16 equals 1. That has to be true because that's our constraint. Okay? You guys following on? You're okay with this? So look, from we'll call this equation A, equation B, and equation C. From equation A, we get lambda equals what? 36y over 2x, right? So 18y over x. It's pretty important that you guys catch any mistake I make here, or else it's just going to be a total embarrassment, waste of time, 3-mix type scenario. Okay? From equation B, you get lambda equals what? 32x over y, okay? So then you end up, since both these things are equal to lambda, you say, well, what values for x and y are true so that 32x over y is equal to 18y over x? I'm just kind of working in bad order here. So then you get 18y squared is 32x squared. And let's not solve that for y, because notice we're going to plug that in down here. So let's just solve it for y squared. And you get y squared equals 32, equals, now 32 over 18, right? 16x squared over, thank you, sorry, I missed that part. Is that right? So now, to solve this thing for all three of our variables, you would take this, eliminate the y, so you get x squared over 9 plus, oh, look what's going to happen. The 16s are gone, and you get x squared over 9. Is that right? Equals 1. So 2x squared equals 9. So x squared is 9 halves, and therefore x is equal to 3 over radical 2. I could solve that by plugging it into this one, and you end up getting y squared equals, let's see, 16 times 9 halves divided by 9. You get y squared equals 8, and y equals 2 radical 3, right? No. 2 radical 2. Okay? So then if we wanted to know lambda, we could, but we don't. Those are our coordinates. So the area of the biggest rectangle that we can fit inside of our given ellipse would be 3 over radical 2 times 2 radical 2, so it's 6. Is that right? Oh, yeah, it's 4 times 4, so it's 24. 24. So what we learned was that the biggest rectangle we can fit in there would be 24 units long, which is directly related to our ellipse, which is kind of cool. Okay? Now, you might be wondering, well, what the heck does lambda tell us? What is that value? What is the Lagrange multiplier? Well, I would ask, and I'm going to stop the video here in just a second, but you should read page 924. That's a great example. It's a similar problem that involves not anything geometrically related, but economics. And you will find at the very end that lambda does have a relatively meaningful value. It is called the marginal productivity in that problem. And what it tells you is that if you optimized your output by choosing the right amount of investment for labor and for capital, then at that point, its instantaneous change is about 1/3 of a product per dollar invested. And I'll explain that to you guys live. I hope you made it through the whole video. We made it just under deuce. Have a great afternoon. Can I get a boo? Boo. Class.